Okay, section 16.1, Bronsted acids and bases. This topic is covered a little bit in chapter 4, but not in detail, and we're going to use this theory of acid-base chemistry quite a bit in this chapter and in the next, in these two chapters, 16 and 17. Okay, so what we're going to do here is we're going to begin by thinking about an acid-base reaction, and the example we're going to use is hydrochloric acid dissolved in water reacting with water itself. Interesting, right? The solvent. And that reaction is going to form H3O plus and Cl minus. Okay, now the idea of the Bronsted acid-base theory is that it looks at acid-base chemistry on the idea, based on the idea of what's called the proton donor. The proton donor is the acid. The proton acceptor is called the base. And what you want to do in this section is identify the donor and the base from acid-base chemistry, and then we'll also take a look at the products as well. Okay? Now, the term proton, just to review, is a synonym. It's synonymous with what's called the hydrogen ion. Hydrogen is the simplest element on the periodic table. It was the first element created at the beginning of the universe. It is very, very simple. It is simply a hydrogen atom is a proton, which we represent with a little plus sign, right? It's a little particle. And an electron. And the electron orbits the proton, right? We'll ignore the modern quantum mechanical interpretation of the hydrogen atom, but we recognize hydrogen as a proton and an electron. Now, if you remove the electron from a hydrogen atom, you now have a hydrogen ion. And so if you take the electron off, all you have is a proton. So that's why the hydrogen ion and the term proton are synonymous. They're essentially the same thing. So here's what we do. What you do is you look at the reactant. There's two of them, right? HCl differs from Cl minus by the fact that the HCl has a hydrogen ion and the Cl minus doesn't. The water differs from H3O plus, again, by the existence of an extra H plus in the hydronium. So what has happened is the water has gained an H plus, and the hydrochloric acid has lost an H plus. So the donor is the one that loses it. So this is the donor. The acceptor is the one that gained it. The water gained it, so this is the acceptor. So this would be called the acid, and this one would be called the base. Okay? So acid-base, the donor. So the way you do it is you look at the reactants and the products, and you figure out which one lost the H plus, that's the acid. The one that gained the H plus is the base. Okay? Let me erase all this. Let me show you another example. This turns out is a reversible process. Okay, so this is ammonia on the left side, NH3 dissolved in water, reacting with water. Water, again, is a solvent, but it turns out ammonia can react with water. And it does. And it forms the ammonium ion and a hydroxide ion. Okay. So let's again pair things up. The NH3 and the NH4 plus differ by an H plus. The NH3 has 3 hydrogens. The ammonium has 4 plus a positive charge, so this one gained an H plus. That's the acceptor, that's the base. The water is now OH minus. That means it lost an H plus. That makes it the acid. So we would say that ammonia is the base and water is the acid. Notice that for the first reaction, the one up at the top with HCl and H2O, water is the acceptor of the H plus, and so it's the base. So water is capable of both processes. It can be an acid or base depending on what it's mixed with. Now, that's relatively simple. But now what we want to do is we want to look at these same reactions, and now I'm going to talk about it from the perspective of the products. And this will be important later on. Okay, hydrochloric acid reacting with water to form this H3O plus ion. Do you know what that's called, that ion, H3O plus? Do you remember the name of it? It's called the hydronium ion. Okay, and then this is a chloride ion. The hydronium ion is very important in Bronsted. This is really Bronsted-Lowry, but Bronsted-Lowry acid-base chemistry. The hydronium ion is very important. Okay, so memorize that formula H3O plus. We already decided this one is the acid and that this one is the base. Okay. Now what we want to do is we want to identify the products. We're going to give names to the products. The products in this particular reaction are H3O plus and Cl minus. And here's what we're going to do. We're going to call the products conjugates. Okay? They are formed in this process, so they're called conjugates. So this is a conjugate right here, and this is a conjugate here. But what we're going to do is we're going to label them as a conjugate acid or a conjugate base. And here's how you go about it. Again, you pair them back up based on the difference of an H plus. There's a couple of different ways to do this, by the way. Okay? Imagine the reaction is going the reverse direction. So imagine that it's H3O plus and Cl. I'll leave the states of matter out just for simplicity. HCl and H2O. So this is the reverse, right? That's the reverse reaction. We learned about that in chapter 15. Now, picture it exactly the same way. Pick the two that go together, that differ only by an H plus, and identify which one's the acid and which one's the base. Well, H3O plus has 3 hydrogens and a positive charge. H2O has 2 hydrogens and no positive charge. So that means the H3O plus donated the H plus, which means that it's the acid. The chloride doesn't have any H's. When it becomes a product, it does. It went from negative to 0 charge, so that means it gained an H plus. So that means it's the base, right? The acceptor of the H plus is the base. The donor of the H plus is the acid. So what we're going to do then is we're going to call these conjugates. So H3O plus is a conjugate, and we've identified it as an acid. So it's the conjugate acid. It is an acid if you're considering the reverse reaction. And the same is true for chloride. It is a conjugate. Since it's a product, it's a conjugate. But if we consider the reverse reaction, it picks up an H plus to become HCl. So it's called a conjugate base. Okay? So when you do the analysis of acid-base chemistry using the Bronsted-Lowry theory, one of the things we want to be able to do is to identify which of the reactants is the acid, which is the base, and then on the product side, which is the conjugate acid and which is the conjugate base. So we've done that for this reaction. Now let's try it for the second reaction that we just did a little earlier. NH3 aqueous plus H2O liquid. NH4 plus aqueous and OH minus aqueous. Okay, hydroxide ion, ammonium and hydroxide. Okay, so let's go through it again. We're going to do both the acid-base, conjugate acid, conjugate base. We know these are conjugates, so we can identify that already. Products are the conjugates. It's just an issue of whether they're acid or base. Okay, let's take the NH3 and NH4 plus together. So the NH3 is gaining an H plus, so it's an acceptor, so that means it's a base. So the ammonium has to be the acid, right? If it accepts an H plus, if the NH3 accepts an H plus, that makes NH3 the base. The reverse reaction, NH4 plus, would give up the H plus, so that means it's an acid. And then let's consider water and hydroxide. Well, water became hydroxide, so it was the donor, so that's the acid. The hydroxide is going to be the opposite. It's going to be the base. Okay? So whatever you figure out for a substance, if it's a base, the one on the other side is going to be an acid, and if something is an acid as a reactant on the product side, it'll be the base. So you can do it that way as well. Okay? So definitely try the practice problems, the sample problems, and the checkpoints for this section.